welcome Alyosha Efros, our speaker today. Alyosha is one of the most influential researchers in a couple of different fields in computer vision and computer graphics. In computer graphics, he recently won the new Researcher Award, which is given to one faculty member, junior faculty member in computer graphics each year. So it's sort of the top award in computer graphics for junior faculty. And in computer vision, he has lots of best paper awards and so forth.
Super excited to be here. Thank you very much for inviting me. And I'm going to talk about using lots and lots of visual data. First, I want to get to make sure that people kind of appreciate why we need data in vision and in graphics. And this is my motivational image. This is Claude Monet, Gare Saint-Lazare. It's one of my favorite paintings by Monet. It's a really kind of nice example of early Impressionist style. And you can really feel like you're at this Parisian train station, at the turn of the century. And you can really kind of sense the hustle and the bustle and all the. We can talk about all these associations, all the impressions that we can make from this image. But the curious thing is, if you look carefully, closely at what is it that is making this impression, for example, if we zoom in on that steam engine right here, we realize that it's not really a steam engine, is it? It's more like a penguin or a bottle of champagne stuck in a cooler, right? Where is the steam engine? This bunch of brush strokes. The thing is that the steam engine is not really in the pixels. It's in our heads. And in fact, probably every one of you, when you see this painting, you have a slightly different version of that steam engine, maybe connected to your childhood experiences in steam engine museums or whatnot. Much of what we see is not really through our eyes. It's really through our memory, that the actual pixels is just a part of what makes the visual experience for us. It is also what we have already seen before. I found this quote. I think it's attributed to Lance Williams. It kind of goes even bigger. It says, "Mind is largely an emergent property of data." I'm not sure it's, I would be that categorical, but I think in computer vision it has taken us maybe 30 years to really realize how strongly of a factor this is and how important this is. Because, most of the time, computers are shipped tabula rasa, right, without any memories. And this means that anything that is so easy for humans, any kind of a recognition or visual understanding task that's easy for humans, it's unfairly difficult for a computer because the computer doesn't have all those memories, all of that data. Okay? So basically, all of my career, I have been working on many different parts of computer graphics and computer vision, but they're all been the line going through all of this has been trying to use a lot of visual data to solve the problems. So things I've been working in inferring 3D from a single image, a bunch of other things, but it's really always was about trying to get the data to help out. And what we found is that in most of those projects, the more data you put in, the better it works, and also the simpler the algorithms need to be. And so in that sense, I thought that it's maybe interesting to talk about just what does it mean to deal with large collections of visual data, big visual data. What can it do for us, and what are the hard things about it? Okay? And so I'm going to start with a kind of very old project that I think it really illustrates the benefits of using big data. And that's basically a work I did on texture. Texture is when you have a bunch of stuff, bunch of the same thing on an image, like bunch of radishes, bunch of rocks, a bunch of yogurt, right? You don't say a yogurt, but it's a. So in that sense, even though it's a single image, there's actually a lot of examples of the same thing in that image. So it's, in a way, it's kind of a big data in miniature, okay? And so what we wanted to do is to synthesize more of it. Given a piece of texture, we wanted to get more texture, but we don't want to get something like this, because that looks too repetitive. We want something like this, okay? And the standard approach at the time was this kind of a classic, maybe you would think of like a parametric machine learning approach. You know, you take a bunch of samples, you analyze them, you try to squeeze out the unimportant stuff and keep only the important bits of the data into some sort of a parametric model. And then once you have this model, oh, you're good, you can sample from that and you create lots and lots of more data, as much as you want, okay? So that's kind of the classic pipeline. The problem is that this squeezing out is very, very hard. Because at the time when you're looking at the data, it's very hard to figure out which bits are the important ones, right? And it's very easy to throw out something that turns out to be extremely important, okay? And for that reason, these kind of methods, you know, they were doing okay, but they weren't really making very good results because the models were just not fitting as well to the data as they could. And so what we decided to do is a much simpler idea, basically a non-parametric method where we keep all the data around and we just sample from the data and create our resulting images from scratch. And so here is just a one-slide summary of the whole thing. It's very, very simple. Given that you have a bunch of pixels already synthesized, how do you synthesize pixel P? Well, you just go to the input image, and you just find similar-looking neighborhoods, and you just randomly take one and put it into P, and you're done. And then you just do this one pixel at a time, boom, 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 and then you can synthesize that. And the cool thing is that this extremely dead simple algorithm was working quite a bit better than all the other kind of fancy schmancy parametric and semi-parametric algorithms that try to somehow capture the data, right? And for a while, I was kind of, okay, well, this looks good, but it's kind of unsatisfactory. It doesn't really tell us anything about the process that we're modeling. It's just, yeah, cutty-pasty, right? But I have later realized that actually there's something deep and interesting in this type of methods working very well. And it's basically one way I explain it to myself is that there are really two kinds of things in our world. You know, there are the kind of things that are nicely modeled with elegant, beautiful math, right? And this is what kind of science was all about, you know, in the golden age, you know, Enlightenment. You know, it was all about trying to find a simple, beautiful formula to explain some really, really complex phenomena, right? And so, for example, we have, you know, you have smoke, and it's, you know, it's extremely complicated thing. And then, but then you can come up with some sort of a explanation of that is, okay, it's still complicated, but it's somehow beautifully explains concisely this large, complicated thing. Okay, so that's that, and we have done very well in that part of the world. We have done very well to try to explain this part of our world, but there is another part of the world where we haven't been doing so well. And that part of the world, it's less physical and more evolutionary, so to say. For example, the pattern of bark on this tree, right? You can perhaps write down a parametric equation for the pattern of this bark. This bark depends on so many things. It depends on the genome of the tree, right? That has a lot of junk, lots of garbage, lots of stuff that was just there just because of entropy. There is no other reason, but just things just happen, right? So there are a lot of parameters in there. There is also kind of the effects of where this tree was, weather, location, you know, whether a squirrel, you know, roosted on this tree or not, right? There's all these things. So if you take all of these parameters together, there will be a lot of parameters. So your model is basically, it's very hard to make it, even if you can make it, it's going to be very hard to make it be a good representation of the actual data, right? On the other hand, for this kind of data, we also have tons of examples of that data. You know, just go search for bark on Flickr, and there's tons of examples of that bark. And so the argument here is that maybe we can just use the data directly in a non-parametric way and make it work better for us. And this is basically kind of a similar argument is being made in this wonderful short paper called The Unreasonable Effectiveness of Data. And basically their argument is, yes, there is a bunch of stuff where elegant mathematics does the trick, physics, chemistry, astronomy, but there is other parts that these elegant methods don't work. Psychology, genetics, economics. We know that people in Wall Street, they thought that economics could be modeled with beautiful mathematics, but it didn't quite work, right? And I claim that image understanding, a lot of it at least, is in that category. And this is exactly where the magic of data happens. This is exactly where having lots and lots of data, even when you don't have a beautiful model, can get you a lot of the way there. And of course, there have been advances in several fields. Speech recognition is one, machine translation, and of course, Google. Google is the ultimate thing. Right? Google is the AI for the postmodern world, right? It doesn't need to create anything. It just looks it up. So, and even though there is no model, you can do all these beautiful things. It's like, my favorite example, you type in climb stairs, you misspell climb, right? And you just put E instead of a B. And it says, did you mean climb stairs? Okay, well, that's not exciting. Even Microsoft Word can do that. But if you say crime and punishment, the same misspelling, it says, did you mean crime and punishment? So suddenly, it looks like Google has been reading Dostoevsky, right? Which, of course, it hasn't. Right? So there's no Dostoevsky model here, but the data, suddenly the data starts to speak to you, right? And this is exactly the type of thing we want to do for visual data. This is exactly the behavior we want. We want the data to start to speak to us. And so this is the good news, right? The good news is that really stupid algorithms plus lots of data gets you unreasonable effectiveness, right? Sometimes. The Economist is warning about the data deluge. There's all this data that's being thrown at us, and really much of this data that is being thrown at us is visual data. You have probably heard all these statistics about Facebook and Flickr, how many images, how many videos, right? So YouTube says 72 hours of video uploaded every minute, right? That means that a lot of those pixels will never be seen by a human being, right? They go from void to void, right? And so, in fact, Cisco estimates that in a couple of years, 90% of net traffic will be visual, right? So a lot of that data deluge that we are talking about, at least in terms of size, is going to be coming from visual data, images, videos, that kind of stuff, okay? And you would think that, okay, all this data, we can do stuff. But if you look at kind of, the big data analytics that everybody's talking about now, there's all this stuff that people look at: economic data, business data, medical data, scientific data, web text, all this stuff, except where is visual data? Nobody's really seems to be looking at that, right? It's kind of, Pietro Pirone calls it internet's dark matter. Piece of the internet that's just, we can't access it, we can't index it. It's just, it's not connected to anything. It's just out there. So the reason for this, and the bad news of this whole enterprise, is that visual data is very difficult to handle, okay? For example, text is clean, it's segmented. We have nicely segmented text into words, so segmentation problem is not there. It's compact, it's 1D, it's indexable. Visual data, it's noisy, it's unsegmented, it's high entropy, it's 2D or 3D, and it's a lot of the times it's very hard to index. Okay? What I mean, basically, the biggest problem is computing a distance between two elements, two items, two entities. So if in text, for example, you can say, okay, what's the distance between climb and crime? Well, you can just do, Hamming distance, and then it's, one letter difference. That's easy. If you have some sort of Euclidean distance, then you can just compute Euclidean distance. If you have, a dark pixel and a light pixel, that's not a problem either. You can just compute the difference between those two values. But what about this? What's the distance between that thing and that thing? Nobody knows. Okay? So it's really the problem is that there is no way for us to figure out how similar are these two pictures. Well, on one hand, they should be pretty similar because they're both penguins, right? And they're both kind of similar pose. On the other hand, every single pixel here on these two pictures is probably different. It's actually, these two images probably don't have a single pixel in common. So if you do something like Euclidean, it's going to be a complete mismatch. So how do we deal with this issue? It turns out to be extremely hard. Now, of course, a lot of you are thinking, wait a minute, this couldn't be so bad because there is all this amazing work being done that uses visual similarity. In fact, this is two of my most favorite projects of all time, the phototourism and the face bios that are both done here at UW, that are actually able to connect visual data together, and you can do lots of wonderful things. Now, the issue here is that here it's been we have the way that this is done is by picking domains where the distance metric is somehow have been figured out. Whether we're talking about architectural domain or the special case of faces, we actually know how to do nice distance computations in these domains. And for the few domains where this is possible, great results are possible. So this is the kind of thing that already works for these domains. But what I'm excited about is to try to make these kind of things work for all of visual data, for general visual data, right? Then you can say, well, isn't like Google Goggles doing that? Well, Google Goggles is very cool, and I use it all the time when I go to the wine store to figure out how many points on Wine Spectator a particular wine bottle is. But again, what it's doing, it is basically a very well-tailored application when you're looking for essentially an exact match that you can do in a reasonable way. So here is an example of the same kind of Google approach in action. What if I want to find an image that's very similar to this? I go to Google Image Search. This is a new search by image feature. You just drop the image in, click, and then you get a whole bunch of beautiful, very similar image examples. Okay, so this is all great, but the way it works is by what's called indexing, what's called visual words. Okay, so the idea here, and this is what, for example, Steve's work on phototourism uses as well. It's very popular. Very popular method of indexing visual data invented by David Lowe up in Vancouver. So what you do is you find a bunch of features in your image, and then you quantize them into kind of a little patches that happen often, and then you see in a new image whether these patches fired there as well. Okay, so you can see why it's called visual words, because it's basically you're representing an image by a bunch of kind of words that instead of being written, they're visual ones, and then you just look at them in the other image, and how if you found many matches, then it's a good match. If you have found few, that's not a good match. Okay, so and it works really well for these kind of examples where you find patches and you find matches between the images. And so, oh, look, this is a beautiful match. It's all these visual words that are matching from one image to the other, right? But what if I give you another image? So this is the same place, it's just different season, slightly different viewpoint. And we do visual word matching, and it completely doesn't work, okay? And the reason it doesn't work is because these things are very local. These visual words, they're very localized. So they are really looking for something that's small and really almost an exact match. So they do very well when you have almost nearly identical things. As soon as something starts to go a little bit off track, as something goes a little bit different, these things, they don't have the power to capture it. So really I would call them not visual words, but visual letters. because they're really kind of these very small things. It's like, you go to Google and instead of typing best croissants in Seattle, and you get good results, you type in, I want a bunch of S's, a few T's, a few E's, and maybe a couple of other letters, right? That's kind of what this thing is doing, right? It still works when you really got it exactly right, right? But you need to get completely right for this to work. Otherwise, you get something like this. So this is another image of a Medici fountain that I took. It's in the winter, so it doesn't snow that much in Paris. So there is not that many images in the database, and so basically it couldn't find good matches to the other images. Or if we want to find matches to something like this, which is a painting of the same place, well, then it's really not working very well. Yes, or maybe a sketch. Well, then it really gets very embarrassing, right? So you can see that actually, you think that it's working, but it's really only working when things are really, really nice and close. And as soon as you kind of take a little step away, then things, you realize like, okay, this algorithm is really doesn't really know what it's doing, right? So this is basically the issue that all of computer vision faces, is that we don't know how to make these correspondences. And I think the best way to kind of to explain where we are right now is with a quote by Jorge Luis Borges in one of his stories, Funes de Memorias. It's about a young kid who has he's on the autistic spectrum, and he says, it irritated him that a dog at 3:14 in the afternoon seen in profile should be indicated by the same noun as dog at 3:15 seen frontally. My memory, sir, is like a garbage heap. Okay? That is exactly, I feel, what we have with visual data right now. Right? We have all of this data. It's all there. But it's not connected. It's just sitting by itself. You have all this knowledge, but you can't really do anything about it because it's largely sitting by itself, except for a few specialized domains. Okay? And so how do we deal with this garbage heap? And so in my view, the things that we need to be doing are, first, we need to find the right visual correspondences across this data. We need to wait to find out whether a pair of images correspond, whether they're talking about the same thing or different things. If we have that, we can then do general mining of visual data, just like they do mining of textual data. And then we can also do something even more exciting, which is to connect visual data in kind of a way, we call it the visual memics, which is kind of this big graph of everything, just like there is a hypertext graph in text. We can try to do this for the visual data as well. Okay, so that's kind of the big plan that I think we as a community need to solve. And of course, different people kind of poking at different parts of this plan. And I will just talk about some of the things that we have been doing. So, what's the simplest way to improve the correspondence problem? The correspondence problem is clearly the key one for making everything else work. And, well, one way to improve it is, so let's say this is your data. And let's say that this is the dog from the quote below, right? And this is the dog at 3:15, and you don't know to connect it to a dog at 3:14, okay? Because the distances, it's too far. Everything else looks too far, right? So the simplest thing we can do, just get more data. Get a closer dog. Get it so that the distances are small enough that you can trust your distance metric no matter how crappy it is. And once you can do that, then hopefully you can kind of bounce around transitively and you can connect everything to everything, right? So that's one way to do this. And we have done one work with my former student, James Hayes, that tries to do this in the context of graphics. Let's say we have an image, and let's say we don't like a piece of it. So we erase it with Photoshop brush. Okay? Now we have an image, and we have a hole. can we fill this hole with something that looks reasonable? Well, what we do is we describe this image, gradients at various scales and orientations, histogram them, and this is essentially the scene gist descriptor proposed by Oliver and Teralba. And then we just get ourselves a couple of million of images from Flickr and just search for this for a similar image in our big data set, okay? And then see what we find. And here's one thing that we found that seemed pretty similar, and then we put it in, we do some computer graphics magic, and it doesn't look too bad, okay? So that's basically it, right? The whole algorithm is just nearest neighbor and a little bit of brush up with computer graphics, okay? And it works pretty well. It works surprisingly well. And we were very surprised, and we said, okay, why does it work? Is it that we have this amazing descriptor, or is it that we have this really cool way to blend it? Well, it seems that it's really all about the data, right? So you have an image right here. This is the query image. We tried this on 20,000 images, and it really did not work. Okay, and I was very kind of disappointed, and I was telling James, okay, it's not going to work. But James, to his credit, he said, okay, I'm going to work on this. I think we just need more data, just more data, and it's like 3 weeks before SIGGRAPH, and say, oh, just let's download for 1 more week, right? And so we download, and then he got to 2 million, and boom, suddenly it just started working. Exactly the same code, okay? Nothing has changed about the algorithm. It just, there was this kind of a threshold, this discontinuity where suddenly the data started to talk to us. Right? We just heard this in the lab. Ooh, the data speaking to us. Okay? So I think that is kind of the key idea. So here are some examples of what else we can do. Say you don't like the hill view from your house. You can get a better hill view. There's a crane there. You don't want this crane. That's no problem. Get rid of the crane. That's pretty cool. So why is it working so well? Let's look at under the hood and see what's going on. So here are the nearest neighbor matches that we found. And let's look at the top match. This is the top match right here. Look at that. So what can we tell from this example? Well, basically that we have two things, independent things going for us. One thing is that we, as people, are kind of boring as far as architecture, right? This is 2 different cities, 2 different rivers, and still it kind of looks the same, right? So we have this regularity, because if you really think about it, all the possible pictures in the universe, that's a huge set. And yet, if you have a city and a river, chances are there's going to be a view something like this. The other half is that imagine that you're a tourist, and you're walking in a city, and you're walking across a bridge, and you turn right, and you look, nice view. Let me take a picture. Says you and 10,000 other tourists, right? So the first thing tells us that there is going to be a view like this in most cities. The second tells us that if there is a view like this, some tourists are going to take picture of it. Okay? And so these two things make this actually not such a hard problem, even though if you look at just all the possibilities of all the possible views of all the possible things in the world, it's a tremendously hard problem. Okay? But in this case, this is what's helping us. Okay? So that's just adding more data and letting kind of the biases of the problem kind of take care of the details is one very simple way of dealing with this. But what if you add more data and you have a bunch of data and you keep adding more data, but there is still an area of the space that doesn't get enough data? No matter how much you add, it's still not enough. Right? So this is kind of the case of the long tail distributions. There is the long tail, right? So this is the problem that the rare is actually common. The idea is that there is a few things that are very common, like this, river view, okay? And so there is a bunch of things like that that are very generic, and there is a lot of them, okay? But then there is also a bunch of things that are kind of rare, kind of unusual, right? But the problem is that there is a lot of these rare things, right? Every one of them is rare in its own way. And so if it was a nice normal distribution, then these kind of rare things would die off pretty quickly. But the long-tailed one means that there is a lot of these rare things. So you can't really just ignore them because, you know, altogether they're pretty heavy. They're a big chunk of the data. So how do we deal with this? Well, so one way we try to deal with trying to get our correspondence to do a little bit better is to see if we can connect visual imagery across different visual domains. Something like across different seasons, or maybe different types of like painting or a sketch. Can we get something that makes this work better, makes our distance metric go farther than it does right now, okay? And so let's look at what we need to do for this. Let's say that this is a painting, and we want to find examples for similar examples for this painting, and we can go to some sort of a retrieval engine, and we can get a whole bunch of retrievals, and we realize that you know, the first retrieval is okay, maybe it's okay, the horizons match up at least. But this one, you know, what is the computer thinking, right? Why did it do this, right? And well, the thing is that the computer is really trying really hard. It can't read your mind, because the computer is saying, okay, there is nothing in my data set that is just like this image. So I'm just going to find something that will make my master somewhat pleased with something. So it found that this area there and this area there, those two textures, they look pretty similar. So it found, okay, I'm going to make these things match somehow, and then hopefully this is what the person wanted, okay? And of course it's not, right? But it's not the computer's fault, because it just doesn't know what is the thing that you're thinking of when you're talking about similarity, okay? Because imagine that if somehow you were to tell the computer, okay, I'm really interested in this castle, in this temple in the center. It would find perfectly good matches for you, because they are in the data set. The data set contained these correct matches. It's just that the computer didn't think that that was the important part of the image to be focusing on, to really match it, okay? So how can we have the computer guess what is it that we're interested in a given image? What is it that is important for us, the humans, okay? Well, in general, we don't know. But one kind of a hypothesis that we had was maybe what we are interested in are the things that are kind of special about this image, that don't really, that are rare, that are uncommon, right? So because in this image, you know, the sky, you know, probably there are many other skies, you know, the tree happens a lot too, but you know, it's the stuff, the temple is the stuff that's really rare. So can we somehow try to capture this intuition? And so what we did is we get a whole bunch of just random images from the internet, and we asked ourselves, what is it about this image that's special compared to a whole bunch of images on the net, right? What is it that makes this image special? And if we thought about this a little bit, and we realized that actually this is very similar to problems that people in machine learning do all the time, right? You basically have class A, that image. You have class B, basically all the other images in the world, and you're trying to figure out what is it that separates the two the best? What is it about class A that makes it most different than class B? So it's basically, you can think of it as a classification problem. which is what we did. We just turned this into a classification problem. It's not a very standard classification problem, because usually you have big class A and big class B, and they're kind of the same size. But here, class A is just one thing, and class B is basically everything else. But turns out that you can still do this, and we applied just a standard SVM, linear SVM to this problem, and we're able to essentially get a weighting, because it's a linear SVM, you can get a weighting which says what are the dimensions of the input that best separate the input image from the rest of the data set. And then we can just use that to order our data set based on that. Okay? So we used an SVM, but there have been a couple of papers last year that says, oh, you can improve of this. It doesn't, you can make it much faster if you use something simpler like an LDA, for example, a Fisher discriminant or something like this. So this I think this kind of ideas are picking up based on this work already. And so we now have kind of a better way to compute distance, to compute the similarity. So here is an example, another example, input query. And this is the representation. We used hog representations. This is kind of a map of representation of the standard representation. And this is the best nearest neighbor in that sense. And this is kind of the output of the SVM, the learned weights of that representation. And it just seems to work much better. Okay? And so here is some more examples. This is the input painting, and this is the kind of the baselines that we ran, and this is our approach. And you can see that it works pretty well between painting and images, where a lot of things are different, right? It's very different things. So here's some other examples. We also plugged it in with the sketch data. Okay, so exactly the same algorithm, nothing changed. But it's just sketches. So this is the baseline, and this is the results of our approach. Some more. Some cute things that we can do it, because this is a SIGGRAPH paper. You have to do some cute things. So one cute thing is that there is this idea of rephotography, right? Which is really cool. You can go and buy this, then and now, like then and now Seattle, right? Finding photographs that are old and matching them to what that place looks like now. Okay, so here is one example of South Station in Boston, an old one, and we wanted to see, how would it look like now. So in fact, you can do that. You can basically go there and take a picture, and there is also some kind of a improved version of this that folks at MIT did, that allows you to control your smartphone or your camera to kind of really align the two images and really find the right way to connect them. And then once you do, then you can get these kind of a then and now rephotography thing, and then you can publish your rephotography book. But this requires going to Boston, flying to Boston, and really finding that place, and then sitting there and trying to find out the right place to take the picture. And we thought, we already have all this data on the internet. Why not use that? So we take this image, and we go to the to Flickr, and we just search for everything in Boston, and then we do just nearest neighbors for all of those 10,000 images in Boston, find the best match, and we got something like this, okay? Which is somebody already took that image, and we just found it, right? So it's kind of it's kind of Googling visual data, right? Instead of creating new content, we just find content that was there all along. It's just that nobody could have found it before. Okay. Another application we call this painting to GPS is, let's say you have a painting and you want to know where the painter was standing when he painted this picture. Well, again, we have lots of Flickr data. We can just let all the matches vote on a map. Okay, you can see that the biggest vote is at that location, which seems to be kind of the right match. And so you can see here is another example. This is Sydney Opera House, go ICCV, and we basically find where are the best matches on the map, and then we put it into the Street View interface, and then you can kind of click on them and see where are the best matches, and then we can kind of zoom in and say, okay, where is it? Ah, there it is. Very good. Now we can go to step 2, which is let's see if we can mine visual data. Okay? One of those images is from Paris. Clap is, you think it's this one? Clap, you think it's this one? Look at that. Okay, for bonus points, where is that? Look at that. You guys are very good. So people are just really, really good at this task, right? Even though this is not like some famous place. It's not like Eiffel Tower or anything. This is just some random place from Google Street View, okay? And yet, somehow, we know what it is, right? And so we actually had a user study, and we tested a bunch of subjects, and people were really, really good. It's 80% accuracy, right? And we asked them, how did you know? What was it that that made you think that this is Paris? And they said, well, you know, the street sign. If you've been in Paris, the street sign is very Parisian. Of course, the window with the kind of the French railing, the balcony, those kind of things. And so we thought, is it possible to find these kind of, to discover, to mine the kind of visual data that we can find automatically that tells us whether something is visual attribute of Paris or not, okay? And so kind of the goal is, given a large geotagged photo data set, to automatically discover visual elements that characterize a geographical location, okay? So the hypothesis is that that kind of visual elements that capture Paris, first, they need to be frequent, right? They have to occur frequently in Paris. Second, they have to be discriminative. That is, they should not occur much outside of Paris, okay? So you can really think of it as kind of TF-IDF for those text retrieval people, right? It's very much TF-IDF, except you don't know what your words are. You don't know what your elements are. You're trying to figure this out at the same time. So why do you need both? Well, if you just use discriminative, you know, this is the most discriminative image of Paris, okay? But it's the only one. So for most photographs, it's not going to do much for you. Most frequent thing in Paris is pavement, and that's not good either, okay? So you need a nice kind of thing with both. And so to do that, we got a whole bunch of, basically we scraped all of Google Street View of Paris, and then for good measure, a whole bunch of other cities to kind of to use against Paris, okay, to see what it's not Paris, okay? And yeah, the Google Street View data is absolutely fantastic. I recommend it to everyone. And all this data, and we basically were able to extract clusters of visual elements, something like this, okay? That's the kind of results that we are looking for. How can we get these kind of clusters? Well, the first thing is basically we assume that what we want is these discriminative and frequent clusters to somehow be clustering in our space of descriptors. So, for example, the hope is that in a high-dimensional space where we represent these, there is a kind of a tight clump where all of the Parisian windows live, right? And we want to find that clump, okay? Now, when you think about clustering, the first thing everybody thinks of, okay, let's just do k-means, right? And the k-means, it's okay, but it's not great because, you know, it will give you some clusters that are pretty good, something like this. But this is trees. We don't want trees because trees are not very geoinformative. But the cluster that we really want, it doesn't work very well. It basically just k-means screwed it up. And the reason it's screwed up because our descriptor is very, very high dimensional. It's like 4,000 dimensions. And for thousands of dimensions, k-means doesn't work very well at all because it just doesn't know. Again, it's the same problem. It doesn't know which of those thousands of dimensions are the important ones. What is it that you are talking about, human? You know, I don't know. There's all these dimensions. There's something about these things that is, you know, looks similar to the computer, but it's just not what we are thinking of, okay? And so what we decided to do here is to instead try to do, instead of clustering everything kind of top down, we try to see if we can kind of discover and sieve things from the bottom up. So the idea is to first add all our negative non-Paris data in there, so we can quickly get rid of things that are not likely to be in Paris, and or that not likely to be representative of Paris. And then, so something like this gets rejected because these trees happen in Paris and not in Paris. And then for the rest of the data, we just start with getting a potential cluster basically started at every point, or nearly at every point. We start as many clusters as we can, and then we try to see which ones of them are likely to be both frequent and discriminative. And kind of slowly, we get rid of all the junk and kind of this needle in a haystack. We start with a lot of potential needles, and then the true needles kind of bubble up to the top. Okay, so that's basically the idea, and the algorithm is, again, very, very simple. The first step is we just start with a whole bunch of input patches of our data, and we just look at nearest neighbors. And you can see that it doesn't look that great. The nearest neighbors here are not doing a very good job. But now we used our little weak bit of supervision. We can say, let's resort these results by how often do the nearest neighbors retrieve a result that's in Paris. Okay? What is also kind of a nice bonus is that visually the matches look much better. The nearest neighbor matches here look much better than the nearest neighbor matches here. Okay? The reason for that is just that if you somehow get all of your nearest neighbors to be from Paris, it's very unlikely that that's an accident, right? Its chances are that they're also matching to the same type of thing, right? It's very unlikely that you get some kind of a garbage, because if it's garbage, it's random, and if it's random, then it should be 50 Paris, 50 non-Paris. So what we get is we get kind of two things at once, right? We get things that are in Paris, and also we get clusters that are visually looking pretty coherent. Okay? So this is already looking pretty good, and we were all excited, except with our Parisian street sign that we really wanted to get. It was ranked very, very low. Okay? And the reason for that is because we looked at it, and you see that this is the input patch, and it gets a few Parisian signs, but then the rest is garbage. Okay, so it was ranked very low. Okay, but here we have the same issue that we had before, that actually we shouldn't be blaming the computer. The computer was doing the right thing. It's just that it doesn't know what we were thinking, because actually these are perfect nearest neighbors. They're perfect nearest neighbors for something. What we wanted is we wanted nearest neighbors for the street sign, right? But the computer is thinking of something completely different. Can you see what it is? The what? The line on the right, exactly. I mean, look at this. It's perfect. It's what you always wanted, no? See, it's human-computer communication is the problem, right? The computer is doing exactly what you ask it to. It's just the communication is the key. So we can improve communication by saying, look, why don't I tell you that what I really want is I want the matches that happen in Paris to be somehow better weighted than the matches outside of Paris. Okay? So can we kind of separate the good matches that we already have and the bad matches, and basically recompute the distance? Recompute the distance metric so that it's say, okay, what is it that separates those good matches from all of the bad matches? Again, we use a standard linear SVM, nothing fancy there. And what we get is we get, again, a weighting that is a different weighting, and it's a weighting that gets to weight up the things that are in common and weight down things that are not. And then we repeat this whole thing again, and we get something that's better. And then we repeat it again and again and again, and then eventually it stops changing and it gets us the right thing. So that's basically the algorithm. It's kind of iteratively improving the clusters. And there's one little trick. You have to be a little bit careful with doing the cross-validation in the right way. And I can talk to you about the details if you want. It's a very simple trick, but it really makes it work. And so then the results, this is random images of Paris. And these are the kind of clusters that we are able to discover. And you can see that they're all visually coherent. And you can see this is just some examples of them, that they're really capturing at least a lot of what kind of makes us think of as Paris. And we tried it in American cities, and it wasn't as good. And we thought, OK, the kind of distinct in cities, San Francisco, Boston. So in Boston, it found those kind of lamps, the gas lamps that are very typical of Boston. But then a lot of it is still kind of cars and garages and all this driving things, right? So it didn't quite work on there. But for European cities, it works really good. OK, it matches up to kind of architecture descriptions in textbooks. We can also, because we have GPS, we can put it on the map and see where it lands on the map. So for example, this cluster. Look at this. It all happens in the big Grand Boulevards. Saint-Michel, Rue de Rivoli, Saint-Germain. So the big balconies are on the expensive streets. The little things, these are on these little side streets. You can also kind of discover other things that, for example, this little thing, it happens on the right bank in Place des Vosges, of course, right here. But there's also another little thing, the little firing that happens here in Marché Saint-Germain. And we talked to an architect, and he said, this might be an example of an architectural citation. This is much younger Marché Saint-Germain, and the architect might have wanted to cite Place des Vosges as kind of a subtle influence, okay? And these are the kind of things that architects are actually interested in and looking for in architectural studies, okay? You can also do it for different parts of Paris. Different neighborhoods have different prototypical things. You can also do it for kind of zoom it up and say what is prototypical of Europe. So this kind of an arch is prototypical of Europe. This kind of balconies and this kind of balconies. You can also see if you can find correspondences across things. So here is all things that are special to Paris. But what happens if we fire them on other cities? You would think that it will be complete garbage. But actually, it turns out that sometimes, not always, but sometimes, it actually works reasonably well. And then we have a procedure that kind of makes it works even better. And now what we have is we have kind of a more generic detector. And then we can start looking for interesting things that happen across the geographical locations. For example, here you can see how the different balconies of the different cities change. Or this is my favorite one. So here, there is this ledge between the two stories in Paris. And you can see that the ledge is right under the second story window. In Prague, there is a very similar ledge, but it's between the floors. It's not up, it's in between. And in London, they're too cheap, so there's no ledge. Okay? You can also look at a particular cluster and see what happens if you... We have talked about it as a kind of a local visual element, but what happens if we look at its context? And we do this by the simple process that Antonio Torralba pioneered, which is basically looking at computing averages centered on a particular element. So we have this element, and we compute an average of everything that it fires, center on the same thing. And what you can see is the kind of the facade emerging. And then again, we can kind of go and look at comparing the different facades of the different cities. And we can see that, there are quite a bit of differences, right? In Paris, the balconies are always on the third floor. You have, in Paris, the floors are all equal heights because it's all égalité, whereas in Prague, the first floor is the biggest, and then it kind of goes less and less and less. So there's a lot of these kind of cool things that get discovered by looking at this data. Okay, and then we also thought, okay, we can do what makes X look like X in more general case. So we ran the same algorithm on the MIT indoor data set. And then we say, OK, what is, for example, for different categories? And so we can say, what makes a grocery store, or what makes a staircase, or what makes a bathroom, right there, That's my favorite. And incidentally, you know, we also get the best recognition performance on that particular data set. But I think the cooler thing is kind of the visual features that it can discover for us. So what I've talked about is this quest for organizing this garbage heap of visual data. We talked about doing something about visual correspondence. We talked about mining. What's the next step? Well, the next step is to connect the visual data together, okay? And this is work that's been going on in my lab for a number of years, and it's still kind of very much work in progress. The idea of connecting basically connecting all the pieces of visual data together into this big graph. It's like the mimics of Vannevar Bush, but for the visual data. And basically, the idea is that if we can have connection between everything visual that we see, we can interpret new images by just finding an isomorphism of that image to that graph. We basically find, okay, how do I explain this new image with all the visual data I have, right? So it's kind of like the hope is that you would be able to click like on any piece or part of the image, and like in hyperlink, you know, you click and it brings you to the similar things, and then they're all being connected together, and so they're all the context is being computed there. And so this is a, you know, theme for the talk, you know, the next talk, next 10 years. After hopefully that's what's going to happen next. We'll see in 10 years if this was true. And so in conclusion, visual understanding is a very data-hungry process. We need lots of data. Luckily, the big visual data is probably one of the biggest data there is. The problem is it's not well behaved. It's not easily indexable. It's not clear, you know, what is the unit of visual that can be indexed. What's the unit, and the distance metrics are not very good. So what in the work that I presented today, basically trying to solve both of these problems together, finding the right visual word representation and the right metric at the same time. Okay? Thank you.